Hello all, I am Shubham Mir. I am the TA for the MOOC Fiber Optic Communication System and Techniques. Today we will be having a lab demonstration in the Fiber and Quantum Optics lab. In the course we have studied the theoretical aspects of fiber optic communication systems and techniques. Now we will see how those theoretical studies that we have been doing transform into a real world applications, and we will look for various components and we'll demonstrate how simple modulation works as well. So we'll start with the first experiment. As you can see on your screens, the experiment contains a laser diode followed by a patch cord and followed by a power meter. I'll explain each of the components. So the first we have a laser diode. As you can see, it's a black box here. It's a DFB laser. So unlike the conventional lasers which have two mirrors, in this scenario we have gratings which act as mirrors, and they are very wavelength selective, so we can actually obtain a very narrow band wavelength, and this actually lasers at around 1550 nanometer, which is the standard wavelength around which fiber optic communication happens, because the loss at that particular wavelength, around that band of wavelength, is minimum, which is around 0.2 dB per kilometer. And the patch cord, it's the yellow cord. It's a single mode fiber. It's 50 centimeter in length. As you can see, it's pretty sturdy. And then we have a power meter which has an inbuilt photodiode. So the purpose of this experiment is to show you how as we slowly increase the laser current, we see that there is a dramatic increase in power after a certain threshold. So that's how a normal diode would also operate. So as I'll show you. So this is lasing at 1550 nanometer. That's very important to note. And as we slowly, on almost a ramp-like increase to the current, we'll see that the power is increasing, but it's not dramatically increasing. There's no knee-jerk increase in the power. As you can see, it's minus 30 dBm, minus 29 dBm, minus 23 dBm, minus 27, and we have around 36 milliampere current. So as we further increase, so this is around where we see that it directly jumped from minus 57 to minus 12, and as we further increase, so this is where the threshold is starting to happen, and as we further increase, we can actually achieve around 0 dBm, and it can go even higher. To keep in the safe limits, we'll just go around 0 dBm. So this was the first experiment. So the purpose of this experiment was to show you how, as increasing the current, we can see a threshold, and we can actually, the power would increase linearly, and the slope of the graph, if we extrapolate to the x-axis, where the x-axis would be the current of the laser diode, we can actually find the exact threshold value. Now we come to the second part of today's demonstration. So instead of the laser diode which we manually controlling the current, we can actually have a programmable laser source where we can actually control the amount of power. Even the wavelength can also be automated by programming the laser current and the cavity length. So the first component is a tunable laser source, as I mentioned, and the second component, as you would have seen in the slides, which is the 3 dB coupler. So 3 dB coupler is, if you have to make an analogy, it's a power splitter as well as a power combiner. It's a 3 dB means half power, so it's a 50-50 coupler. And so if we have an input coming, it would actually split the input into equal halves. So we can see the current input power to this fiber spool, which I'll explain next, is 0.48 dBm. And equal amount of power is also going in the other arm, so which is in the fiber spool, which would again be 0.48 dBm. And so this is a 50 kilometer fiber spool. So what we're going to do is we are actually going to measure the amount of power loss in this fiber spool, and we'll try to show you that when we say that the fiber loss is around 0.2 dB per kilometer, so if we can measure the net loss over a 50 kilometer fiber, then we can calculate what would be the actual loss of this particular fiber spool. So since we now know that the input power is 0.48 dBm, please keep that in mind. you can write it, probably write it somewhere. And so if I disconnect it and I'll just take a cab. And connect it to the output of the fiber spool, and I'll show you what the power is, and then we'll finally make a. So the input power was 0.48, and as you can see, the output power is minus 9.52 dBm, which is, if you were to actually, if you can see the, so which is minus 9.5 dBm. So the input power is 0.448 dBm and the output power is minus 9.52 dBm. If you were to subtract the net power, which would be around 10 dB, which is very, very close to 10 dB, there is slightly more loss which can be attributed to the connectors here, these connectors, these FCBC connectors. So as you can see, the net loss can be approximate to almost 10 dB. So what does that mean? So we have 50 kilometer fiber and the net loss we are observing is 10 dB. So the per kilometer loss of the fiber is 0.2 dB, which is the number that we have been providing you in the lectures. And so this specific loss is around the wavelength of 1550 nanometer, and it's one of the low, so this low amount of loss per kilometer actually helps us to employ optical fibers over long distance communication. So we come to the final part of this demonstration. As you can see on your screens, we have the final setup, which contains a laser diode, a polarization controller, an MZM, which is a Mach-Zehnder modulator, which has an RF input from the function generator, and a sampling oscilloscope. So we would like to give an introduction before we proceed to actually see these components. So as we have already seen laser diode, we have a DFB laser diode, and I've already explained that component. Next we follow it with a polarization controller. We'll see in a moment what polarization controller looks like. So the polarization controller, the function of the polarization controller allows us to modify the polarization state of light. So it contains 3 plates, which is a quarter wave plate followed by a half wave plate and a quarter wave plate again. So by modifying the angles of the plates, we can actually control the polarization of the light. So it works on the stressed induced birefringence by wrapping fiber around the 3 spools in the three paddles respectively. So then the next component, we have a Mach-Zehnder modulator. So the one that would be present in the lab is a lithium niobate based optical modulator. So the lithium niobate crystals are actually, the refractive index of these crystals are a function of the strength of the local electric field, and we have these crystals in a Mach-Zehnder modulator configuration. So as we vary the voltage across these crystals in a push-pull configuration, as already discussed in the lectures, we can actually achieve intensity modulation. And the other thing is they are polarization sensitive. So it's imperative for us to have a polarization controller before the optical modulator. And then we have a function generator which actually provides an RF input. So this can be pulses, this can be our data, or this can be in fact a modulated data as well. And the last component in the slide that you can see is a sampling oscilloscope. So sampling oscilloscopes are actually different from the standard digital storage oscilloscopes. They are based on sequential sampling, unlike real-time sampling in the standard digital storage oscilloscopes. So in a conventional digital storage oscilloscope, what we'll have an ADC, and it will sample each cycle, and it's limited by its speed, and it would have consecutive samples periodically. But however, in the sequential sampling, we'll vary the timing of the sample over each cycle of the waveform, and over a number of cycles we can actually reproduce the waveform in the sampling oscilloscope. So this actually allows us to use low speed ADCs, which are just limited to sampling the waveform data at 1 sample per cycle. So that's the limit of the ADC that we can have, and we can actually over a time we can actually have a reproduction of a high bandwidth signals, and so we can actually go up to 20 gigahertz even though the ADC might be at a lower speed. So that sampling oscilloscopes in that sense helps us to actually capture waveform data at even a higher frequency as compared to standard digital storage oscilloscopes, which are limited by the speeds of the ADC itself. Now we come to the setup here. I'll run you through all the setup that we have here. So first we have the standard DFB 1550 nanometer laser diode. Then we move on to polarization controller. So as you can see, it has 3 paddles as I mentioned. So this is a polarization maintaining fiber. So in each of this paddle, the fiber is wrapped around these spools, and we can actually have stress induced birefringence. And so as we will vary these angles of these paddles, we can actually change the polarization of the light. And the next is the Mach-Zehnder modulator. So it's, if you can zoom in on this, it's inside this box. It's very compact, and so it's not bidirectional, it's unidirectional. So we need to take care of where to provide the input and where to take the output from. And then there is an RF signal that is being applied through this function generator. We are actually applying a 400 megahertz signal, and so it goes into a power splitter, and like one part goes into the Mach-Zehnder modulator, the other part we use for triggering the oscilloscope, which I'll also explain in a moment. And then we have another patch cord connecting the output of the Mach-Zehnder modulator to the wideband oscilloscope. So currently there is no data, but we'll just get the data. So in the function generator, as we can see, we have a 400 megahertz input signal to the Mach-Zehnder modulator, and it actually modulates the incoming optical input to the Mach-Zehnder modulator, and as we can see, it goes into the oscilloscope, which has a photodiode, and we can actually recover those pulses. As you can see, the reading here is 400 megahertz, which is around that. As if you can see that, we actually recover a sinusoidal RF input as a sinusoidal optical input. So this actually shows how a basic modulation of the optical input can be done. And the another important thing is that this Mach-Zehnder modulator, as I previously mentioned, is polarization sensitive. So now if I were to vary the angles of the controller, we'll see that the optical input actually starts coming down. So this shows the polarization dependency of the input to the Mach-Zehnder modulator. So it's important for us to have a polarization controller beforehand, so we can align the incoming light polarization according to the axis of the Mach-Zehnder modulator itself, which is a lithium niobate crystal based Mach-Zehnder modulator, and this modulation is on the basis of the electro-optic modulation effect. And there are other types of modulator as well, but lithium niobate gives you a very high frequency performance, and a good dynamic range as well. To conclude, we did 3 experiments today. I showed you how a 1550 nanometer laser diode operates, and then we moved on to the loss measurement of a 50 kilometer fiber, and as we have seen in our lectures itself, that the loss measured is around 0.2 dB per kilometer, and in the lab conditions we can actually show that the loss came out to be 0.2 dB per kilometer, hence agreeing with the theory. And we also saw what various component looks like and how compact the technology, the fiber optic technology has become, and how commercialized it is, and how mature the technology has become over a period of time. And also the last, we actually showed a very simple modulation. We actually had an RF input of a sinusoidal wave of 400 megahertz. Then we provided this modulation, RF modulation input to the Mach-Zehnder modulator, which had an optical input, continuous optical input coming. So because the refractive index of the lithium niobate crystal changed according to the electric field, which the electric field was provided by the RF signal itself, we could actually see that the modulation, because of the push-pull configuration of the Mach-Zehnder modulator, the optical input was intensity modulated, and then we connected to a sampling oscilloscope. We actually also saw what's the difference between a sampling oscilloscope and a real-time oscilloscope, and we have actually recovered precisely the RF input that we were sending, which was a 400 megahertz sinusoidal input, and we are recovering a 400 megahertz sinusoidal input. And also, if we were to vary the frequency, we'll see that that frequency would be reflected on the oscilloscope itself. So if I were to make 400 as, let's say, 800 megahertz, this is a very basic modulation scheme. We have a sinusoidal input to the MZM, and in practical applications we actually go to even higher order modulations. Then we have I and Q arms modulation, this is which is for QARM and QPSK modulation schemes. Thank you.